BONGARD, a new benchmark for human-level concept learning and reasoning. Weili, Rice University donate at rice.eg NVIDIA, Zidinga at NVIDIA Danga, Leimao at NVIDIA.com. Ankit B. Patel, Rice University of Religion and Medicine, AP4 at rice.edu. Yuki Ju, UT Austin, NVIDIA at CSU Texas.edu. Animashri Anand Kumar, Caltech, NVIDIA, Anima at caltech.edu. Abstract. Humans have an inherent ability to learn novel concepts from only a few samples and generalize these concepts to different situations. Even though today's machine learning models excel with a plethora of training data on standard recognition tasks, a considerable gap exists between machine-level pattern recognition and human-level concept learning. To narrow this gap, the BONGARD problems, BPs, were introduced as an inspirational challenge for visual cognition in intelligent systems. Despite new advances in representation learning and learning to learn, BPs remain a daunting challenge for modern AI. Inspired by the original 100 BPs, we propose a new benchmark, BONGARD LOGO, for human-level concept learning and reasoning. We develop a program-guided generation technique to produce a large set of human-interpretable visual cognition problems in action-oriented logo language. Our benchmark captures three core properties of human cognition. 1. Context-dependent perception, in which the same object may have disparate interpretations given different contexts. 2. Analogy-making perception, in which some meaningful concepts are traded off for other meaningful concepts. And 3. Perception with a few samples but infinite vocabulary. In experiments, we show that the state-of-the-art deep learning methods perform substantially worse than human subjects, implying that they fail to capture core human cognition properties. Finally, we discuss research directions towards a general architecture for visual reasoning to tackle this benchmark. Introduction. Human visual cognition, a key feature of human intelligence, reflects the ability to learn new concepts from a few examples and use the acquired concepts in diverse ways. In recent years, deep learning approaches have achieved tremendous success on standard visual recognition benchmarks. In contrast to human concept learning, data-driven approaches to machine perception have to be trained on massive datasets, and their abilities to reuse acquired concepts in new situations are bounded by the training data. For this reason, researchers in cognitive science and artificial intelligence, AI, have attempted to bridge the chasm between human-level visual cognition and machine-based pattern recognition. The hope is to develop the next generation of computing paradigms that capture innate abilities of humans in visual concept learning and reasoning, such as few-shot learning, compositional reasoning, and symbolic abstraction. The deficiency of standard pattern recognition techniques has been pinpointed by interdisciplinary scientists in the past several decades. Over 50 years ago, M. BONGARD, a Russian computer scientist, envisioned a new benchmark for human-level concept learning and reasoning. A/B test freeform shape problem, A/B test basic shape problem, A/B test abstract shape problem. Three types of problems in BONGARD LOGO, where the freeform shape concept is a sequence of 6 action strokes forming an ice cream cone-like shape. The basic shape concept is a combination of fan-like shape and trapezoid. The abstract shape concept is convex. In each problem, set A contains 6 images that satisfy the concept, and set B contains 6 images that violate the concept. We also show 2 test images, left positive, right negative, to form a binary classification task. All the underlying concepts in our benchmark are solely based on shape strokes, categories, and attributes, such as convexity, triangle, symmetry, etc. We do not distinguish concepts by the shape size, orientation, and position, or relative distance of 2 shapes. Scientists invented a collection of 100 human-designed visual recognition tasks, now named the BONGARD problems, BPs, to demonstrate the gap between high-level human cognition and computerized pattern recognition. Several attempts have been made in tackling the BPs with classic AI tools, but to date we have yet to see a method capable of solving a substantial portion of the problem set. BPs demand a high level of concept learning and reasoning that is goal-oriented, context-dependent, and analogical, challenging the objectivism embraced by traditional pattern recognition approaches. Therefore, they have been long known in the AI research community as an inspirational challenge for visual cognition. However, The original BPs are not amenable to today's data-driven visual recognition techniques, as this problem set is too small to train the state-of-the-art machine learning methods. In this work, we introduce BONGARD LOGO, a new benchmark for human-level visual concept learning and reasoning, directly inspired by the design principles behind the BPs. This new benchmark consists of 12,000 problem instances. The large scale of the benchmark makes it digestible by advanced machine learning methods in modern AI. To enable the scalable generation of BONGARD-style problems, we develop a program-guided shape generation technique to produce human-interpretable visual pattern recognition problems in action-oriented logo language, where each visual pattern is generated by executing a sequence of program instructions. These problems are designed to capture the key properties of human cognition exhibited in original BPs, including context-dependent perception, in which the same object may have fundamentally different interpretations given different contexts; analogy-making perception, in which some meaningful concepts are traded off for other meaningful concepts; and perception with a few samples but infinite vocabulary. These three properties together distinguish our benchmark from previous concept learning datasets that centered around standard recognition tasks. In our experiments, we formulate this task as a few-shot concept learning problem and tackle it with the state-of-the-art meta-learning and abstract reasoning algorithms. We find that all the models have significantly fallen short of human-level performances. This large performance gap between machine and human implies a failure of today's pattern recognition systems in capturing the core properties of human cognition. We perform both ablation studies and systematic analysis of the failure modes in different learning-based approaches. For example, the ability of learning to learn might be crucial for generalizing well to new concepts, as meta-learning methods largely outperform other approaches in our benchmark. Besides, each type of meta-learning methods has its preferred generalization tasks, according to their different performances on our test sets. Finally, we discuss potential research frontiers of building computational architectures for high-level visual cognition, driven by tackling the BONGARD LOGO challenge. BONGARD LOGO benchmark. Each puzzle in the original BONGARD LOGO set is defined as follows. Given a set of 6 images, positive examples, and another set of 6 images, negative examples, the objective is to discover the rule or concept that the images in the positive set obey and the images in the negative set violate. The solution to a BONGARD LOGO puzzle is a logical rule stated in natural language that describes the visual concept presented in all images of the positive set, but none of the negative set. The original BONGARD LOGO puzzles consist of 100 visual pattern recognition problems of black and white drawings. Through these carefully designed problems, BONGARD aimed to demonstrate the key properties of human visual cognition capabilities and the challenges that machines have to overcome. We highlight these key properties in detail in the next section. From a machine learning perspective, we can have multifaceted interpretations of the BONGARD LOGO puzzles. Pioneer studies cast it as an inductive logic programming (ILP) problem and a concept communication problem. These two formulations typically require a significant amount of hand engineering to define the logic rules or the language grammars, limiting their broad applicability. A more general and learning-oriented view of this problem is to cast it as a few-shot learning problem, where the goal is to efficiently learn the concept from a handful of image examples. We are most interested in this formulation, as it requires the minimum amount of manual specification and likely leads to more generic approaches. In the following, we introduce our benchmark that inherits the properties of human cognition while being compatible with modern data-driven learning tools. Benchmark overview. We developed the BONGARD LOGO benchmark that shares the same purposes as the original BONGARD LOGO puzzles for human-level visual concept learning and reasoning. Meanwhile, it contains a large quantity of 12,000 problems and transforms concept learning into a few-shot binary classification problem. Some examples in BONGARD LOGO are shown in the text. For example, in one case, set A contains 6 image patterns which are all convex shapes, and set B contains 6 image patterns which are all concave shapes. The task is to judge whether the pattern in the test image matches the concept, e.g., convex versus concave, induced by set A or not. As the same concept might lead to vastly different patterns, a successful model must have the ability to identify the concept that distinguishes set A and set B. The problems in BONGARD LOGO belong to three types based on the concept categories. Free-form shape problems. In the first type of problems, we have 3,600 free-form shape concepts, where each shape is composed of randomly sampled action strokes. The rationale behind these problems is that the concept of an image pattern can be uniquely characterized by the action program that generates it. Here, the latent concept corresponds to the sequence of action strokes, such as straight lines, zigzagged arcs, etc. Among all 3,600 problems, each has a unique concept of strokes, and the number of strokes in each shape varies from 2 to 9, and each image may have 1 or 2 shapes. To solve these problems, the model may have to implicitly induce the underlying programs from shape patterns and examine if test images match the induced programs. Basic shape problems. The other 4,000 problems in our benchmark are designed for the basic shape concepts, where the shapes are associated with 627 human-designed shape categories of large variation. The concept corresponds to recognizing one shape category or a composition of two shape categories presented in the shape patterns. Similar to the free-form shape problems, each problem has a unique basic shape concept. One important property of these problems is to test the analogy-making perception, where, for example, zigzag is an important feature in free-form shapes but a nuisance in basic shape problems. Abstract shape problems. The remaining 4,400 problems are aimed for the abstract shape concepts. Each shape is sampled from the same set of human-designed 627 shape categories. Action programs. An illustration of the context-dependent perception in BONGARD LOGO, where the concept is have 4 straight lines, and the concept is have 6 straight lines. The same shape pattern, highlighted in red, has fundamentally opposite interpretations depending on the context, whether the line segments are seen as continuous when they intersect with each other. 2 exemplar shapes and the action programs that generate them procedurally, where each base action, line or arc, has 3 arguments, from left to right: moving type, moving length, and moving angle. Note that there are 5 moving types, including normal, zigzag, triangle, circle, and square, each of which denotes how the line or arc is drawn. Both values of moving length and moving angle have been normalized into 0, 1, respectively. The purpose of these problems is to test the ability of abstract concept discovery and reasoning. There are 25 abstract attributes in total, including symmetric, convex, necked, and so on. Each abstract attribute is shared by many different shapes, while each shape is associated with multiple attributes. Due to the increased challenge of identifying the abstract concept, we randomly sampled 20 different problems for each abstract shape concept. An example of abstract shape problems is shown in Figure 1C, where the underlying concept is convex. Similarly, the stroke types, i.e., zigzags or lines of circles, etc., do not impact the convexity. Large variations in all convex and concave shapes ensure that the model does not simply memorize some finite shape templates, but is forced to understand the gist of the convex concept. Properties of the BONGARD LOGO problems. In the BONGARD LOGO problems, we do not distinguish concepts by shape size, orientation and position, or relative distance of 2 shapes. Furthermore, the BONGARD style reasoning needs the visual concept to be inferred from its context, with a few examples. All these together demand a perception that is both rotation invariant and scale invariant, and more importantly, a new learning paradigm different from traditional image recognition methods. In the next, we mainly focus on 3 core characteristics of human cognition captured by BONGARD LOGO and use intuitive examples to explain them. 1. Context-dependent perception. 2. Analogy-making perception. And 3. Perception with a few samples but of infinite vocabulary. Context-dependent perception. The same geometrical arrangement may have fundamentally different representations for each context on which it arises. For example, the underlying concept in the task of Figure 2a is have 4 straight lines. Straight line segments must be seen as continuous, even when they intersect with another line segment. This does not happen in the task of Figure 2b, where intersections have to split the straight lines to fulfill the underlying concept have 6 straight lines. Another representative example is the hierarchy in concept learning. An equilateral triangle can either be interpreted as equilateral triangle or as convex, which completely depends on what the remaining positive images and negative images are. This property is compliant with the so-called one object, many views in human cognition, where the existence and meaning of an object concept depend on human understanding. Inspired by the original BPs, our benchmark contains many examples that require context-dependent perception. PXC, where C is the context to which an object X belongs. It does not make sense to infer the concept from X alone, as there is a need for contextual information outside of X. Most current pattern recognition models are implicitly context-free. For example, image classification models take a single cat image and output a cat label without referring to any other image as context. They assume that objects exist in reality outside of any understanding, and the goal is to find the unique correct description. Therefore, the perception of an object should be C. In the conventional context-free models, there is a one-to-one mapping from any object X to its unique representation Px. This might be responsible for the inefficiency of current pattern recognition models based on context-free perception in our benchmark. When humans make an analogy, they interpret one object in terms of another. In this sense, representations can be exchanged. A zigzag can be interpreted as a straight line, or a group of triangles as an arc, or any other object as something else. When we exchange a zigzag for a straight line, we not only interpret it as such, but also attribute all straight line properties to it, like straightness. Though zigzags can never be straight, we can easily envision a zigzagged line and a zigzagged arc, as depicted in Figure 1. Numerous problems in our benchmark necessitate an analogy-making perception. An example is shown in Figure 1b, where the underlying concept involves a trapezoid, even if some trapezoids lack straight lines, instead being a collection of circles or zigzags forming a trapezoid-like shape. This is essential since when addressing a task, we trade one concept for another. Perception with a limited set of examples but an infinite vocabulary is different from standard few-shot image classification benchmarks. There is no finite set of categories or standard geometrical arrangements in BONGARD LOGO. In BONGARD LOGO, rather than dealing with recognizable shapes like triangles or circles, many freeform shape problems are challenging to explain without context. An example of freeform problems is demonstrated in Figure 1a, where the name of the shape is hard to provide, but it can still be recognized by observing the strokes to classify novel test images correctly. Each freeform shape comprises randomly sampled basic stroke structures, making the shape vocabulary size infinite. The infinite vocabulary prevents memorization of geometrical arrangements but focuses on the ability to conceptualize. This aligns with human visual cognition principles, where concepts are inferred from a few examples and applied to various situations. A key feature of the original BONGARD problems is that a visual concept can be communicated implicitly and concisely by comparing two sets of image examples. The generation process is scalable, as shapes are procedurally created in the Logo language, where a turtle follows procedural action commands to produce vector graphics. These action programs offer supervision, aiding symbolic reasoning in the action space, and can potentially enhance methods utilizing symbolic stimuli, such as neurosymbolic AI. The vocabulary of base actions are of relatively small size, making the concepts compositional in the action space and much easier to generate. To simplify the process, we use only two classes of base actions, line and arc. As each base action has three arguments, moving type, moving length, and moving angle, an action is depicted by a function, action name, moving type, moving length, moving angle, as shown. Specifically for the above arguments, there are 5 moving types, including normal, zigzag, triangle, circle, and square. For instance, normal means the line or arc is perfectly straight or curved, zigzag means the line or arc is of the zigzagged style, and triangle means the line or arc is formed by a set of triangles. Besides, both moving length and moving angle are normalized into the range of 0, 1, where 0 and 1 correspond to the minimal and maximal values, respectively. Depending on varying lengths of action programs, different combinations of these base actions form visually distinct shapes. Our benchmark contains different types of shapes, each of which requires a separate procedure in the logo language to generate, and we leave generation details. We have open-sourced the procedural generation code and data of BONGARD logo. Experiments methods. We consider several state-of-the-art approaches and test how they behave in BONGARD logo, which demands human cognition abilities. First, as each task in BONGARD logo can be cast as a two-way six-shot, few-shot classification problem, where meta-learning has been a standard framework, we first introduce the following meta-learning methods, with each being state-of-the-art in different, i.e., memory-based, metric-based, optimization-based meta-learning categories. 1. Snail, a memory-based method. 2. Protonet, a metric-based method. 3. Meta-opnet and Anil, two optimization-based methods. As the meta-baseline is a new competitive baseline in many few-shot classification tasks, we consider its two variants. 1. Meta-baseline SC, where we meta-train the model from scratch, and 2. Meta-baseline MoCo, where first use an unsupervised contrastive learning method, MoCo, to pre-train the backbone network and then apply meta-training. Besides, we consider two non-meta learning baselines for comparison. One is called Ren-BONGARD, a variant of Bo-Ren that was originally designed to encourage reasoning in the Raven-style progressive matrices, RPMs. Another one is a convolutional neural network, CNN baseline, by casting the task into a conventional binary image classification problem, which we call CNN baseline. Benchmarking on BONGARD logo. We split the 12,000 problems in BONGARD logo into the disjoint train validation test sets, consisting of 9,300, 900, and 1,800 problems respectively. In the training set and validation set, we uniformly sample problems from 3 problem types in section 2.1. To dissect the performances of the models in different problem types and levels of generalization, we use the following 4 test set splits: free-form shape test set, basic shape test set, combinatorial abstract shape test set. Methods: train ax test, AFF test, BA test, ac NV. Snail 59 2 months 1 F553 NS 3 damp 6.2366 no 1 mas 3.161 0.8. Protonet 733.30 now just forward 660 set 74862 1 band 365 damn force 1 band 2. Meta opnet 75.9003663 now 67 17 2 band 4. 1.7.9 3 10.9 annual 60 and 7.6.6 1 and 2 don't open 9 5 d16671a. Pyda's 1.5 meta baseline SC 75.4 knows 106 6.3 0.673 plus 133.5 0.3639 plus 0.8. Meta baseline MoCo 81.2 0.165.9 so 472.2 0.839 BN864. Remember BONGARD node 78.77 and 7.1.1 and is 1.055.6. CNN baseline 61.4 and A5 1.5666. 2.953.6, 2.057.6 plus and 0.7. Human 92.1 7 99.3 1.9 90.7 plus 6.1. Human amateur 8.7.7 91 1.71.0 and 9.6. The 20 novel combinations are exclusive in the test set. The rationale behind this set is that understanding the abstract shape concepts requires a model's abstraction ability, as it is challenging to conceptualize abstract meanings from large shape variations. Novel abstract shape test set. This test set, NV, includes 320 abstract shape problems. Our goal here is to evaluate the ability of a model on the discovery of new abstract concepts. Different from the construction of the combinatorial abstract shape test set, CM, we hold out one attribute and all its combinations with other attributes from the training set. All problems related to the held-out attribute are exclusive in this test set. Specifically, we choose have 8 straight lines as the held-out attribute, since it presumably requires minimal effort for the model to extrapolate, given that other similar have XXX straight lines attributes already exist in the training set. Quantitative results. We report the test accuracy, ACXC, of different methods on each of the 4 test sets respectively, and compare the results to the human performance in Table 1. The experiment setup for training these methods can be found in Appendix C, and the results are averaged across 3 different runs. Performance analysis. In Table 1, we can see that there exists a significant gap between the human expert performance and the best model performance across all different test sets. Specifically, human expert can easily achieve nearly perfect performances, 99% test accuracy, on the basic shape BA test set, while the best performing models only achieve around 70% accuracy. On the freeform shape FF, combinatorial abstract shape CM, and novel abstract shape NV test sets where the existence of infinite vocabulary or abstract attributes makes these problems more challenging, human expert can still get high performances, 90% test accuracy, while all the models only have around or less than 65% accuracy. The considerable gap between these SOTA learning approaches and human performance implies these models fail to capture the core human cognition properties. Comparing human, expert, and human amateur, we can see human, expert always achieves better test accuracies with lower variances. This advantage becomes much more significant in the abstract shape problems, confirming different levels of understanding of these abstract concepts among human subjects. Comparing different types of methods, meta-learning methods that have been specifically designed for few-shot classification have a greater potential to address the BONGARD logo tasks than the non-meta-learning baselines. In Table 1, we can see the better test accuracies of most meta-learning models across all the test sets, compared with the non-meta-learning models. Interestingly, REN, the model for solving RPMs, suffers from the severest overfitting issues, where its training accuracy is around 78%, but its test accuracies are only marginally better than random guess, 50%. This manifests that the ability of learning to learn is crucial for generalizing well to new concepts. Furthermore, we perform an ablation study on BONGARD logo, where we train and evaluate on the subset of 12,000 freeform shape problems in the same way as before. As there are no properties of context-dependent perception and analogy-making perception strongly presented in these freeform problems, concept learning on this subset has a closer resemblance to standard few-shot visual recognition problems. We thus expect a visible improvement in their performances. This is confirmed by the results in Table 2 in Appendix C, where almost all the methods achieve better training and test performances. Specifically, the best training accuracy of methods increases from 81.2% to 96.4%, and the best test accuracy of methods increases from 66.3% to 74%. However, there still exists a large gap between the model and human performance on freeform shape problems alone, 74.5% versus 92.1%. It implies the property of few-shot learning with infinite vocabulary has already been challenging for these methods. We then compare different meta-learning methods and diagnose their respective failure modes. First, meta-baseline MoCo performs best on the training set and also achieves competitive or better results on most of the test sets. It confirms the observations in prior work that good representations play an integral role in the effectiveness of meta-learning. Between the two meta-baselines, we can see that the MoCo pre-training is more effective in improving the training accuracy, but the improvements become marginal on the test sets. This implies that the state-of-the-art unsupervised pre-training methods improve the overall performance while facing severe overfitting issues. Second, we perform another ablation study on model sizes. The results in Figure 5 in Appendix C show that the generalization performances of different models generally get worse as model size decreases. Besides, most meta-learning models perform much better on the basic shape problems than on the abstract shape problems. This phenomenon is consistent with the human experience, as it takes a much longer time for humans to finish a latter task. How to improve the combinatorial generalization or extrapolation of abstract concepts in our benchmark remains a challenge for these models. We also observe that each type of meta-learning methods has its preferred generalization tasks according to their different behaviors on test sets. For example, the memory-based method seems to try its best to perform well on abstract shape problems by sacrificing its performance in the freeform shape and basic shape problems. The metric-based method performs similarly to meta-baselines and better than memory-based and optimization-based methods. Lastly, the optimization-based methods tend to have a larger gap between training and test accuracies. These distinguishable behaviors on our benchmark provide a way of quantifying the potential advantages of a meta-learning method in different use cases. Few-shot learning and meta-learning have the goal of learning a new task from a small amount of training data. Pioneer works have approached it with Bayesian inference and metric learning. A rising trend is to formulate few-shot learning as meta-learning. These methods can be categorized into three families: 1. Memory-based methods, 2. Metric-based methods, and 3. Optimization-based methods. Recent work has achieved competitive or even better performances on few-shot image recognition benchmarks with a simple pre-training baseline than advanced meta-learning algorithms. It also sheds light on a rethinking of few-shot image classification benchmarks and the associated role of meta-learning algorithms. Concept learning methods concern about transforming sensory observations and experiences into abstract concepts, which serve as the building blocks of understanding and reasoning. A rich and structured representation of concepts is programs that model the generative process of observed data in an analysis by synthesis framework. Program-based or rule-based methods have been applied to tackle BPs. RF4 is an ILP system where the images are hand-coded into logical formulas. FEICO is an exemplar BP solver that implements the FARG concept architecture, proposes to translate visual features into a formal language with which the solver applies Bayesian inference for concept induction. However, these methods require a substantial amount of domain knowledge and do not offer complete solutions to original BPs, making them infeasible for our benchmark, which consists of tens of thousands of problems. In contrast, is the first work to show the usefulness of deep learning methods for solving BPs by using a pre-trained feature-extracting neural network. All these results motivate the development of hybrid concept learning systems that integrate deep learning with symbolic reasoning, which have attracted much attention recently. The hybrid systems can offer great potential in combining the representational power of neural networks with the generalization power of symbolic operations for tackling our benchmark. Abstract reasoning benchmarks. In addition to popular machine-machine perception benchmarks that focus on categorization and detection, there have been previous efforts in creating new benchmarks for abstract reasoning, including compositional visual question answering, physical reasoning, mathematics problems, and general artificial intelligence. Most relevant to our benchmark, the Raven-style progressive matrices, RPMs, a well-known human IQ, have inspired researchers to design new abstract reasoning benchmarks. Our benchmark is complementary to RPMs. RPMs focus on relational concepts such as progression, XOR, etc., while BONGARD LOGO problems focus on object concepts such as stroke types, abstract attributes, etc. In RPMs, the relational concepts come from a small set of 5 relations. In our benchmark, the object concepts can vary arbitrarily with procedural generation. Recently has proposed VRPM that extends RPMs to real images. As VPROM is a real image version of RPMs, it differs from our benchmark in the similar ways described above. Therefore, in contrast to RPMs where automated pattern recognition models have achieved competitive performances, our BONGARD LOGO benchmark has posed a greater challenge to current models due to its fundamental shift towards more human-like, i.e., context-based, analogy-making, few-shot with infinite vocabulary, visual cognition. Discussion and future work. We introduced a new visual cognition benchmark that emphasizes concept learning and reasoning. Our benchmark, named BONGARD LOGO, is inspired by the original BPs that were carefully designed in the 1960s for demonstrating the chasms between human visual cognition and computerized pattern recognition. In a similar vein as the original 100 BPs, our benchmark aims for a new form of human-like perception that is context-dependent, analogical, and few-shot of infinite vocabulary. To fuel research towards new computational architectures that give rise to such human-like perception, we develop a program-guided problem generation technique that enables us to produce a large-scale dataset of 12K human interpretable problems, making it digestible by data-driven learning methods to date. Our empirical evaluation of the state-of-the-art visual recognition methods has indicated a considerable gap between machine and human performance on this benchmark. It opens the door to many research questions. What types of inductive biases would benefit concept learning models? Are deep neural networks the ultimate key to human-like visual cognition? How is the BONGARD-style visual reasoning connected to semantics and pragmatics in natural language? Prior attempts on tackling the original BPs with symbolic reasoning and program induction have also been far away from solving BONGARD LOGO. However, along with the inherent nature of compositionality and abstraction in BPs, they have supplied a great amount of insight on the path forward. Therefore, one promising direction is to develop computational approaches that integrate neural representations with symbolic operations in a hybrid system that acquires and reasons about abstract knowledge in a prolonged process that establishes a tighter connection between visual perception and the high-level cognitive process. We invite the broad research community to explore these open questions together with us for future work. Broader impact. Our work created a new visual concept learning benchmark inspired by the BONGARD problems. Our preliminary evaluations have illustrated a considerable gap between human cognition and machine recognition, highlighting the shortcomings of existing pattern recognition methods. In machine learning and computer vision, we have witnessed the integral role of standardized benchmarks in promoting the development of new AI algorithms. We would encourage future work to develop new visual cognition algorithms towards human-level visual concept learning and reasoning. We envision our benchmark to serve as a driving force for research on context-dependent and analogical perception beyond standard visual recognition. We believe that endowing machine perception with the abilities to learn and reason in a human-like way is an essential step towards building robust and reliable AI systems in the wild. It could potentially lead to more human-interpretable AI systems and address concerns about ethics and fairness arising from today's data-driven learning systems that inherit or augment the biases in training data. A potential risk of our new benchmark is that it might skew research towards highly customized methods without much applicability for more general concept learning and reasoning. We encourage researchers to develop new algorithms for our benchmark from the first principles and avoid highly customized solutions to retain the generality and broad applicability of the resultant algorithms. Acknowledgements and disclosure of funding. We thank the anonymous reviewers for useful comments. We also thank all the human subjects for participating in our BONGARD LOGO human study and the entire AI Algo team at NVIDIA for their valuable feedback. WN conducted this research during an internship at NVIDIA. WN and ABP were supported by IRPA via DOI IBC contract D6TPC3 and NSF Neuronext grant DBI7U forwarded. K. Saito and R. Nakano, a concept learning algorithm with adaptive search, in Machine Intelligence 14, Applied Machine Intelligence, 1996. S. Depueg, C. A. Rothkopf, and F. Jekyll, Solving BONGARD Problems with a Visual Language and Pragmatic Reasoning, Arxiv preprint Arxiv 1804.4452, 2018. D.J. Chalmers, R.M. French, and D.R. Hofstadter, High-Level Perception, Representation, and Analogy, A Critique of Artificial Intelligence Methodology, Journal of Experimental and Theoretical Artificial Intelligence, 1992. A. Linhares, A Glimpse at the Metaphysics of BONGARD Problems, Artificial Intelligence, 2000. H. Abelson, N. Goodman, and L. Rudolph, Logo Manual, 1974. D. Barrett, F. Hill, A. Santoro, A. Morcus, and T. Lillicrap, Measuring Abstract Reasoning in Neural Networks, an International Conference on Machine Learning, 2018. E. Trantafilou, T. Zhu, V. Dumoulin, P. Lamblin, U. F. G. Keshu, R. Groshin, C. Galata, K. Swirsky, P. A. Manzagal, et al. Metadataset, a dataset of datasets for learning to learn from few examples, Arxiv Preper 3-20396, 2019. N. Mishra, M. Rohaninejad, X. Chen, and P. Abil, A Simple Neural Attentive Meta-Learner, ICL 2018. J. Snell, K. Swirsky, and R. S. Zimmel, Prototypical Networks for Few-Shot Learning, Advances in Neural Information Processing Systems 2017. K. Lee, S. Maji, A. Ravichandran, and S. Soato, Meta-Learning with Differentiable Convex Optimization, in Proceedings of the IEEE Conference on Computer Vision and Pattern Recognition, 2019. A. Raghu, M. Raghu, S. Bengio, and O. Vignoles, Rapid Learning or Feature Reuse, Towards Understanding the Effectiveness of Mammal, ICLR 2020. Y. Chen, X. Wang, Z. Lu, H. Xu, and T. Darrell, A New Meta Baseline for Few-Shot Learning, Arxiv Preprint, Arxiv 2003 But 04390, 2020. S. Karagorgiev, Solving BONGARD Problems with Deep Learning, k10v.github.io 2020. M. Lazaro Gradia, D. Lin, J. S. Guntapalli, and D. George, Beyond Imitation, Zero-Shot Task Transfer on Robots by Learning Concepts as Cognitive Programs, Science Robotics 2019. B. Ndurkia, Metaphor in Cognition, An Interactionist Approach, 2013. K.C.J. Holyoke, D. Gentner, and B. N. Kokanov, Introduction, The Place of Analogy in Cognition, The Analogical Mind, Perspectives from Cognitive Science, 2001. Y. Tian, Y. Wang, D. Krishnan, J. B. Tenenbaum, and P. Asola, Rethinking Few-Shot Image Classification, A Good Embedding is All You Need, Arxiv Preprint Arxiv 2003.11539, 2020. J. B. Tenenbaum and F. Xu, Word Learning as Bayesian Inference, in Proceedings of the Annual Meeting of the Cognitive Science Society, 2000. A. Santoro, S. Bartunov, M. Botvinnik, D. Wierstra, and T. Lillicrap, Meta-Learning with Memory-Augmented Neural Networks, in International Conference on Machine Learning, 2016. K. H. Fan, Y. Wu, S. Shi, and R. Gershik, Momentum Contrast for Unsupervised Visual Representation Learning, in Proceedings of the IEEE CVF Conference on Computer Vision and Pattern Recognition, 2020. J. C. Raven, Standardization of Progressive Matrices, British Journal of Medical Psychology, Vol. 19 1, pp. 137 to 150, 1941. El Feifei et al., A Bayesian Approach to Unsupervised One-Shot Learning of Object Categories, in Proceedings 9th IEEE International Conference on Computer Vision, pp. 1134 to 141, IEEE 3. G. Koch, R. Zimmel, and R. Salakutdinov, Siamese Neural Networks for One-Shot Image Recognition, in ICML Deep Learning Workshop, Vol. 2, Lil. 2015. O. Vinyals, C. Blundell, T. Lillicrap, D. Wierstra et al., Matching Networks for One-Shot Learning, in Advances in Neural Information Processing Systems, pp. 3630 to 3638, 2016. M. Wren, E. Triantafilou, S. Ravi, J. Snell, K. Swirsky, J. B. Tenbaum, H. LaRochelle, and R. S. Zimmel, Meta-Learning for Semi-Supervised Few-Shot Classification, ICLR 2018. S. K. Davala, A. Farhadi, and C. Gestrin, Learning Everything About Anything, Webley Supervised Visual Concept Learning, in the IEEE Conference on Computer Vision and Pattern Recognition, CVPR, June 2014. N. Hay, M. Stark, A. Schlegel, C. Wendelken, D. Park, E. Purdy, T. Silver, D. S. Phoenix, and D. George, Behavior is Everything, Towards Representing Concepts with Sensor-Motor Contingencies, in 32nd AAAI Conference on Artificial Intelligence, 2018. H. Foundulis, Fayeko, A Cognitive Architecture Inspired by Bongard's Problems, Indiana University, Indiana, Bloomington, 2006. J. Mao, C. Gan, P. Coley, J. B. Tenenbaum, and J. Wu, The Neurosymbolic Concept Learner, Interpreting Scenes, Words, and Sentences from Natural Supervision, in ICLR 2019. C. Han, J. Mao, C. Gan, J. Tenenbaum, and J. Wu, Visual Concept Metaconcept Learning, in Advances in Neural Information Processing Systems, pp. 5002, Phython 13, 2019. A. Bakhtin, L. Vandermotten, J. Johnson, L. Gustafson, and R. Gershik, Fire, A New Benchmark for Physical Reasoning, in Advances in Neural Information Processing Systems, pp. 583, 594, 2019. K. R. Allen, K. A. Smith, and J. B. Tenenbaum, The Tools Challenge, Rapid Trial and Error Learning in Physical Problem Solving, Arxiv Preprint, Arxiv 1907-0962, 2019. E. Whitenauer and H. Ritter, Physical Bongard Problems, in EFIP International Conference on Artificial Intelligence Applications and Innovations, pp. 157 to 163, Springer, T12. D. Saxton, E. Greffenstedt, F. Hill, and P. Coley, Analyzing Mathematical Reasoning Abilities of Neural Models, Arxiv Preprint, Arxiv 1904.0157, 2019. F. Scholle, On the Measure of Intelligence, Arxiv Preprint, Arxiv 1911-01547, 2019. P.A. Carpenter, M.A. Just, and P. Shell, What One Intelligence Test Measures, A Theoretical Account of the Processing in the Raven Progressive Matrices Test, Psychological Review, Vol. 197, 3, 404, 1990. C. Zhang, F. Gao, B. Zhao, Y. Zhu, and S. C. Zhu, Raven, A Dataset for Relational and Analogical Visual Reasoning, Proceedings of the IEEE Conference on Computer Vision and Pattern Recognition, p. 5377327, 2019. D. Tenney, P. Wang, J. Cao, L. Liu, C. Shen, and A. V. D. Hengel, VPROM, A Benchmark for Visual Reasoning Using Visual Progressive Matrices, in AAAI 2020. M. Kunda, K. McGregor, and A. K. Goel, A a computational model for solving problems from the Raven's Progressive Matrices Intelligence Test using iconic visual representations. Cognitive Systems Research, Vol. 22, pp. 4766, 2013. T. Mitchell, W. Cohen, E. Hrushka, P. Talukdar, B. Yang, J. Betteridge, A. Carlson, B. Dalvey, M. Gardner, B. Kiesiel, et al. Never-Ending Learning. Communications of the ACM, Volume 61, Number 5, pages 103 to 115, 2018. Deha and J. Schmidhuber, World Models, Arxiv Preprint, Arxiv, Whitino 3.1012, 2018. C. M. Bishop, Mixture Density Networks, 1994.